So sigma sends, so sigma being an element of the logarithm of k over f, sends every root of f, so the polynomial with coefficients in x, every root of that in k to, again, a root of the same polynomial. So sigma gives a map from the set of roots of f in k, f is a polynomial with coefficients in f, right? From the set of roots of f in k to the set of roots of the same set. Okay. Right? Sends any root to, again, a root of the same polynomial. It gives you a function from this set to itself. Right? The function being just alpha to sigma of alpha. You know, why don't we just give a notation to this for now? Let's call this sigma. Here, as a subscript, I'm going to write roots, bracket f, roots of f. So this is the restriction of sigma to the set of roots of f. Just any root of f. How acts sigma on the set of roots of f? Okay, and now, well, this is the set of roots of f. Well, that's a finite set. It's got at most as many elements as the degree of f. So the set of roots of f, so this is the set of roots of f. This is what I'm calling the set of roots of f, okay? Roots f, sorry, I just want to make sure I didn't lose the camera. So by this I mean the set of roots of f. This is a finite set. Okay, and now you've got a function from that finite set to itself. And, well, this function here, well, sigma is injective, so this restricted map is also injective. Sigma roots, restriction of sigma to the roots of f is injective because, well, sigma is injective. Right, these are automorphisms, they are isomorphisms. And their domains is actually a field, so they would be injective even if they weren't subjective. Okay, and now putting these two, you see that, well, it's an injective function defined on some finite set, from some finite set to itself, and it's injective. Then it would also have to be surjective. Sigma roots f, sigma restricted to the roots of f is also surjective. So this is a bijective function from the set of roots of f to the same set. So sigma restricted to the roots of f is a permutation of the set of roots of f. Remember what was the definition of permutation? Recall. Given any set x by a permutation of x, we mean a bijective function from x to x. So I just make sure that we're not losing the camera. So sigma, well, permutes the set of roots of f. This was for any polynomial f with coefficients in our field f. Okay, very good. Now, well, let's also introduce a notation here. Notation. Remember the set of all permutations of x, they form a group, right? If you compose two, form a group under composition. If you compose two bijective functions from x to x, you're going to get a bijective function from x to x. The inverse of a bijective function is the identity element is the identity function, and the inverse element is just the inverse function. And if your function is bijective, it's got an inverse function which is also bijective. So the set of bijective functions from x to x, the set of permutations of x, that forms a group under composition. And remember, you had a name for this. You call this the symmetric group on x. I'm going to denote that by S sub x, this for the symmetric group on x. So the group of all permutations. Of all permutations of x. Well, in group theory, I think you were dealing with the symmetric group on the set of numbers 1 to n, and you call that S sub n, right? But in general, given any set x, S sub x, and by that we mean the symmetric group. By that we denote the symmetric group on x, which is the set of all permutations of x, which will be a group under composition. Okay, so what we saw here, so to recap what we have so far, is that if you give me any element of the Galois group of K over F, so we have some field extension K over F, give me any element of the Galois group of K over F, let's take a polynomial F with coefficients in F, that element of the Galois group is going to permute the set of roots of F in K. And by this sigma sub roots f, we denote, well, so the permutation of the roots of f given by sigma. And now, get a map so the polynomial f being fixed, coefficients in f, you get a map from the Galois group of K over F to the symmetric group on the set of roots of F. This is get a map for any F with coefficients in F. You get a map from the Galois group of K over F to sorry, just making sure we have the camera. So you get a map by sending sigma. Well, sigma permutes the set of roots of F. So sigma restricted to these roots of F. So you're just restricting to the set of roots of F, and sigma gives you a permutation of the set of roots of F. And if you wish, you could give this guy a name. Let's call this, if you want, restriction to the set of roots of F. And clearly this is a group homomorphism. This is a right, the operation in both of these things is composition of functions, and you're restricting your function. This is clearly a group homomorphism. Okay, let me stop. Yeah.